Hi, Chinthaka.
Hello, Boby.
So we were playing with the resistive sensors.
We were. I'm wondering what you have here on the screen.
Yeah. So I was thinking what new item I can cook today.
I don't know. It looks like some kind of a probe. I
Yeah.
don't know, like a valve or.
There is some display here.
I can see it.
It's not that visible.
And there's a probe
Yeah.
and some housing.
So yeah, so there is a probe here and some way to fix it to maybe a structure.
Uh-huh.
Maybe it could be a vessel kind of something like this.
Yeah. If you look at the structure,
Yeah.
the design,
Correct.
it seems like, you can kind of insert it or
Insert it.
somewhere or something, I
Yeah.
suppose.
Since you are not able to see this display, I can help you with the unit. Says degree Celsius.
Okay. So, what we see here
Is
is temperature sensors.
yes. Temperature sensor. But how is it working?
You know the best way
Hmm.
to find that out? If you take this apart. And
So-
I know you're an expert in doing
So
it,
cut open and see what is inside.
Exactly. What do you think?
Yeah, that's a nice idea. But I have only a photograph for now.
Have you opened up one of these sensors?
I have, if not this, very similar one I have opened up.
So you know what's inside then.
Yeah.
That that's good enough.
Yeah. So actually I saw a resistive element. It's a resistance. It's a resistor, for example,
Okay.
with 2 terminals. Sometimes I see 3 or 4 terminals. I don't know why. You'll find out later.
Okay.
So there is some resistive element here, and then those connections are brought out here.
Okay. So what does that mean? If there's a resistor, the first thing that pops to my head is what I've seen. Is it changing? Is the resistance changing because of temperature? Because you said there's a resistor.
Yeah.
That's
We know this R is equal to, or Rx equal to rho L by A. This is what we were talking
yes.
about before. But I'm not changing rho, L or A. With temperature, there will be little bit of expansion.
Yes.
But very small.
Yes. And rho is resistivity is
Maybe resistivity.
that's what I'm thinking. Unless temperature changes L and A in a significant manner, which I doubt.
Correct.
Then we are only left with resistivity. So is it something to do with that?
Yeah.
It is.
Yeah. So you are heating if you are measuring temperature, let's say you want to measure the change in temperature. Let's say room temperature is 25 degree and then it increase to 30 degree. Or let's say you want to measure fever.
Okay.
Whatever, Fahrenheit, if you want to measure, somehow the resistivity of the material has to change. That means this resistive element, you have to expose it to the environment.
Yes.
So when I actually opened, I didn't see the resistive element. I saw some package.
Okay.
It's nicely packed. My drawing is not very proper. It is nicely packed inside. And inside you had, there was a resistive element like this. Yes. And this is filled with some material and so on. Okay. So basically very good, material with good thermal conductivity.
Right.
So that means if, whatever be the outside temperature, let's say 30 degree, it will pass on to this resistive element quickly.
So good, like kind of heat transfer.
Yeah. Now, we might have heard about something called temperature coefficient of resistance.
Yes. See?
Temperature coefficient of resistance. Usually some symbol called alpha.
Mm-hmm.
So what it says is, with respect to temperature, the resistance of if you take a metallic resistor, it increases. Yes. Sometimes if we do the same, or if you take semiconductor material, we know when the temperature increases, there will be more free electrons and so on.
Motion.
Yeah. So the resistance actually decreases. Yes. So there can be positive or negative temperature coefficient of resistance for the material. Right. So for example, copper, I just checked. It says it has got 0.004. Alpha. Maybe it's not very clear. So suppose what we said is you have a resistive element made of metal, let's say nickel, or let's say copper. Copper is not really used for forming a resistive element.
Right.
But suppose if you use, with respect to temperature, the resistance of this is going to increase. So there is a very standard relationship. Let's say RT is the resistance that you want to know at temperature T. And if you know its resistance at 0 degrees Celsius,
okay,
let's say that is R naught, right? Then I can write R naught into 1 plus alpha T.
Okay.
So T is the temperature at which you want to, know the value of resistance. R naught is the resistance at 0 degrees Celsius. Okay. We can also modify this equation. I mean, if I know the temperature at T1, what will be the temperature at T2? Right. So in that case, R naught will be that RT1 and T will be T1 minus T2 or T2 minus T2. So what I meant is there is a linear relation that is present between, to take care of the
temperature.
Yeah, change in resistance with respect to temperature. Actually, we have discussed this before.
In strain gauges.
In strain gauge.
And we figured out how to compensate
Yeah,
that,
right.
Get rid of
Exactly.
that dependence
Exactly.
on the temperature.
So there we have formed 4 elements of, having same temperature coefficient of resistance, and all 4 are exposed to same temperature. Yes. So it got cancelled. The average got
got a full Wheatstone bridge.
Yes. So here, instead of that, we are not going to expose this material to strain. Let's say you expose only to temperature. It's actually as simple as that. Change in temperature. Then your Rx or change in resistance is just due to change in temperature. Right. And for every material, for example, for copper, we said is 0.004. For some other material is, it depends on the material. Right.
And its alpha has been found by some sort of experiment.
I think it's technical. Yes. Right. So I was just looking at these. There's some nice write-up, providing, how do you measure temperature, what are the technologies available, and so on. So I found a nice material from Microchip.
So there are different ways other than resistance to measure temperature.
Yes.
Okay.
So resistance change is one of the ways, right?
Is it the most common way?
It's one of the widely used ways. Also, it depends on the application, right? Because some of these materials may not withstand higher temperature, right? Their property may change. It may get, there may be corrosion, things like that.
Just a question. So you said R0 is a temperature at 0 degrees Celsius. So can it go the other way too? Like if you're measuring, let's say, minus 25 degrees Celsius.
Yeah.
Or does that depend on the type of material that we're talking about?
You can go to the negative side also. Right. Yeah. I will show you. I have some examples like that.
Okay.
Yeah. So for example, one of the materials that is kind of widely used is platinum.
Mm-hmm.
So there is, if you search for resistance-based temperature detectors. So it's actually called as RTDs. RTD. resistance temperature detector. It's a resistive element, as I mentioned earlier. Its value changes depending on the temperature. Now, one thing what I mentioned is one of the widely used RTD is PT100. There are also PT1000s and so on.
Okay.
So PT stands for platinum, the material used. 100 stands for, I think it's resistance value at 0.
Oh, okay. Right.
So it will give 100 ohm at 0 degree. And I think platinum has got 0.00385 also alpha. I have that.
A good memory.
No, I may be wrong. You will check that. So that means, as temperature increases, resistance will be increasing and so on. So what I meant is, see, PT100 is one of the widely used, but the question is, why platinum? It's a bit expensive.
Mhm.
Why not copper or something?
Something much cheaper
Yeah.
and widely available.
Yeah, because copper has also got, in fact, a slightly better alpha. What maybe?
Could it be due to the range of temperature that can measure or the accuracy? I mean, these are some things I can
Could be, yeah.
think of.
But platinum, we also know. See, copper, once we expose to atmosphere, there will be some oxidation, correct, and then some layer will form.
Yes.
Correct. So then its thermal properties will also start affecting it, right? So you want some material which is somewhat inert, right?
Unstable.
Yes.
Even after you expose it to the environment.
Yeah. So platinum is something like that. So that's why people thought, even if it's expensive, it's good to have this inert material,
Right.
To use, because temperature, it's not a very friendly environment. For our temperature measurement, our fever measurement, it's okay, but when it goes to 600 degree and so on, yes, it may not be so convenient for the material to stay there.
And especially, I think in electronics,
correct,
I think heat is generally a problem, right?
Yes. Yes.
I guess it
makes
sense.
Yeah. So that is the reason why platinum is used. Also, since you mentioned electronics, something popped up by my mind. If you look at most of the ICs, some of the special ICs, they will say it's a temperature compensator. Yes. Yes. So that means inside the IC, there is some way they are sensing the temperature and then correcting for its effect, right? Because most of the electronics, to reduce the cost, etc., they may go for certain designs, but that may be sensitive to temperature, right? And this may have to, something which is meant for, let's say, military application. It has to be done for a wide range of temperature, right? Then you need to have that kind of compensation, which means again, inside which there is some way they are measuring temperature. It need not be RTD, right?
Yeah, especially in this application like military, as you said, right? You don't want like a high gain or something like this. So, that depends on temperature, right?
Correct.
Which problem. So you're saying inside the IC, there must be something like, we don't know.
Yes.
Some kind of platinum element.
Yeah, it need not be platinum.
Or any kind of temperature compensation.
It need not be RTD. Because for, IC fabrication process, it's good if you can sense that using some PN junction, etc.
Something that can be integrated onto the pipe.
Exactly.
When you're making it.
Exactly.
I see.
Yes. Yeah. Right. Yeah. So that way, not just, since you asked earlier, is RTD is the only way, only sensor that you can sense temperature.
And you've already given examples that.
So this is one of this where you use the PN junction property itself when it is exposed to temperature. if it's a diode, we know it's the diode current is some I naught into e power Vd by Vt, and Vt we know it's Kt by Q.
So then it's direct.
Yeah, so it is a function of temperature, yes. But it's also sensitive, I naught is also sensitive to temperature, we know, but there should be some way to correct for that effect, right, to make the output sensitive to T alone, right. But what we see is the diode voltage Vd is a function of temperature. So that could be one way to sense that
in an integrated circuit.
In an integrated circuit. In fact, there are ICs
that measure temperature.
Specifically to measure temperature alone, right? That also uses the same technique. We will elaborate that in detail later.
But I imagine such temperature sensors can be made very small.
Yes. Yeah.
If you're let's say a PN jacket.
Yeah. Small, but sometimes the package takes some space.
Right.
Yeah. In fact, I've seen smaller size-wise, smaller temperature sensors using long back we studied this Seebeck
Seebeck effect, yes.
So if you have metals of different dissimilar materials, right, if it makes a contact, there is some voltage which is generated.
Yes, due to the different temperature.
Exactly. Yeah. So that's what and then if you have two of such junctions and one junction is kept at a known temperature, you can find out what's the temperature at the other end. Right. So that's what's called thermocouple. I think briefly we mentioned this when the course started.
I think so. Yeah. Initially.
Yeah.
We talked about sensors in general. And we talked about that. I think
because I think that generates a voltage. If there is a difference in temperature, it generates a voltage,
and it's proportional to the temperature that we measure.
Yeah. Correct. So that is another way. And then I said, metals are used, but why not if you use semiconductor? I think briefly now we discussed that also. As temperature increases, there will be more free electrons or poles that will decrease its resistance. So the alpha will be negative. Yes, but usually they are much more sensitive compared to the resistance-based temperature detectors.
You mean the negative value?
Yes. Right. What I meant is if the, with respect to temperature, let's say the PT100 goes this way, the NTC, the negative temperature coefficient based semiconductor material may have huge change like this.
Oh, I see. Okay.
It will be more than this, right? What I drawn is not
more exponential degrees.
Yes,
rather than a linear.
Yeah, so it is much more sensitive. Right.
But you're talking specifically about negative values.
In the value can be positive.
Value can be positive.
Yes.
Okay.
Yeah, for same temperature. Right. Let's say the temperature is increasing from 0. As you increase, our the RTD with positive temperature position, it increases
linearly.
Yes, while the NTC material, the semiconductor material, which has a negative temperature coefficient or resistance, its value decreases at a very faster rate compared to RTD. Now, see, we said here R0 into 1 plus alpha T. This is kind of an approximation because I will show you people have done some study. We will come to that later. Since we briefly discussed about various sensing technologies, one thing is thermocouple, the other one is resistance temperature detector. Yeah, so that's sensitive area for this pen. So I will show, RTD. Yeah, so and the thermistor. Yes, thermistor is the material with, let's say, semiconductor material, right? And then the integrated silicon. We have briefly discussed all this. This is a nice table maybe for students to go through, right?
To understand the difference.
Yeah, to understand the difference. Also, it has given the range of operation. I mean, this is something we discussed in the beginning of the course. Each sensor has got its own range and so on. So if you look at here, RTD, minus 250 to 900 degree.
Oh, that's
That's
pretty
actually a
broad
lot.
range, huh?
That's actually a lot.
Yeah.
But then you look at here, thermocouple, minus 270 to 1800. Right. So actually, if I want to measure, let's say 1700 degree, then RTD is not an option.
Or you're on 1,000.
Yeah, yeah. And of course, the integrated silicon, it's only from minus 55 to 150.
A very narrow range.
Yeah.
Even though, as you said, the signal changes rapidly.
Yeah.
The range is very low.
Yeah. So the signal change rapidly, I mentioned for thermistor, NTC.
Okay. Thermistor.
Yeah.
Okay.
Yeah. Right. The silicon is also good, but it's actually used to, as we mentioned, within an IC, if you want to measure the change in temperature, right? Or if you want to monitor temperature inside a CPU, things like that, right? So there, minus 55 to 150 is perfect, right? So different technologies, and based on that, the range is also different. So thermistor has got minus 100 to 450 only, while it will have more sensitivity. Yes.
So there are trade-offs.
Yes. So like sensitivity, the other factor is that day we discussed linearity.
Yes.
So if you look at, I think the RTD has, we will come to these details later. It says requires a second order polynomial to get a good representation of, see, I wrote 1 plus alpha t. It says it's not enough. I mean, it's enough for some level of accuracy. Yes. If you want better accuracy, you will have to go for a second order polynomial. That is the relation between the resistance and the temperature. Yes. Now, so if you do that, then you can get into this level of accuracy, 0.01. But thermistor requires at least third order.
Oh, right.
So as I've drawn earlier, it's with a straight line you cannot. Right. Maybe even if you add a second order, may not be enough. Third order is required.
Some cubed function.
Yes. And thermocoupled, fourth order. So actually, if you want to use thermocouple, thermistor, etc., relatively, you need a little bit more computation.
So that means it seems like if you look at the range and the order of polynomials, right? The wider the range,
somewhat
the higher the polynomial.
Yeah,
right?
somewhat it is coming
Somewhat,
like that.
yeah.
Yeah, that is true. Yeah. And integrated silicon based one, there is a special configuration that uses two matched BJTs. It gives quite linear range for, linear output for a good range. We'll see that later. Okay. So if you have, linearization circuit, the by design itself, it is like that. So it's only plus or minus 1 degree deviation from the straight line. Right. Other factors, I think maybe students can go through. One thing is excitation. As you can see here, it generates by its own. It says no excitation required. While the RTD requires it, current source it says, could be a voltage source also. So thermistor. Also, these are resistors actually. So change in resistance to measure, you need to have some kind of excitation. Right. And this, we will see this later. From the power supply itself, it derives the power that is required.
So the thermocouple then is definitely a passive sensor because it doesn't require any color.
Yeah. It doesn't require any external source. Yeah. But usually that voltage, what you get from this is small.
Right.
So for you to use it, you may need amplifier.
Right.
So that way.
But that's in the back end of the sensor.
Yes. As a complete unit, it requires power. But the sensing element by itself
is very small, you're saying.
Yes.
Well, what's the most sensitive Boby? Out of all the different.
Yeah. So let's look at here. Sensitivity, thermocouple, couple of, tens of microvolt per degree Celsius.
Here,
Platinum, it's in ohm.
it's in ohm.
Yeah, so it's up to you. Yeah, once you bring in the bridge network to measure and so on. Right. Yeah. Thermistor, actually, these two we can compare because thermistor is several ohms per ohm per degree Celsius. While RTD has got 0.0038. Right.
Thermistor for the most sensitive.
Yes, relatively. It's relative. Yeah. Responsiveness. This one is quite fast. Means, let's say, you want to measure temperature and then you expose the sensor to that environment.
Right.
Take some time to
stabilize.
Yes. Or, see, any material means, let's say, made of even metal. Suppose if we expose it to a temperature of T, and let's say this is time T, it takes some time for the heat to transfer.
Trying to absorb all the
heat. Yeah. So for the material to become of same temperature as that of the environment, it takes some time. So the thermocouple junction is actually very small. So that way,
it's very quick. It's clean and small.
Yeah.
So that means if you are using, let's say, a temperature sensor for, let's say, a feedback kind of loop, control kind of situation, then the thermocouple is probably the best because it responds very quickly.
Yeah. If the response time required is very small, then this is better. Yeah. But in some cases, it need not be that fast. So RTD can be used. Take some seconds. This is also a couple of seconds. This is also, everything else takes time, right?
So it comes nearly 1 minute.
Yeah. So, but in a IC, if you are monitoring, if you are in an integrated circuit, the temperature may not change that fast.
That's right. Correct.
It's already packed inside something and so on. So, quick change in temperature is not, unless otherwise there is a
faulty component or something, and
then there is no point in monitoring temperature also. Yeah. So, it's just to give an overall idea, although we are going to talk more about RTD and thermistors where it's based on change in resistance. There are other technologies that are widely used, thermocouple and integrated silicon. There are also some other technologies which is used. But for now, we will focus on RTD.
Okay. I think it's a very nice table, I think.
Yeah.
Right? And again, when you're designing a sensor system, if you're designing a temperature-based sensor system, right? This is very common, right?
Yes.
You need to compare the different types of options available,
exactly,
right? And you have the different features of each sensor,
yes,
right? So for the students, I think this is a nice way,
exactly,
to compare the different types of
the range, the accuracy, is it linear or not?
Yeah.
How good is its linearity?
Yes.
What's the responsiveness? Type of output, voltage, change in resistance or current and so on. Exactly. Approximate size. And then there was one more column for row. It says the cost, which I removed. Maybe students can refer to that. Right. Because when you select something for certain application, that's also important. Correct.
Exactly.
Yeah.
Especially if you're going to make many of these devices, right?
Exactly.